today's goal is one theorem. I'm sort of doing this. This is not a theorem I would normally do. I have never taught this theorem before. Kind of the only reason I'm doing it is because Tao does it. And I was just about to skip it, and then I started thinking about it. I think it's really neat because it is really like a quintessential like real analysis theorem. Like the way we prove it is really like real analysis. The other thing about it is, it's kind of a question that it's a natural question. We will answer it. But I'll tell you what, this theorem really illustrates why you want to use complex analysis when you can. Now in this course we're not allowed to because this is called real analysis, not complex analysis. So we're going to do it the hard way. If you've seen complex analysis, you might not have even mentioned this theorem because from that perspective it's kind of obvious. Okay? So let me motivate it with what, first of all, what's not our theorem. Suppose you've got two functions, f and g, and they're both equal to power series. We should have some condition for like some open interval. I'm going to center everything at 0. So Monday's lecture, we were centering things at different points because we were talking about analyticity. We're back to just centering everything at 0 and saying that if your series aren't centered at 0, you can just recenter them. Okay? So we're only going to prove our theorem for power series centered at 0. Here is my first question. It's not the theorem. What is the power series for f plus g? Are there any volunteers?
Just a simple sum.
Yeah.
Yeah.
So the function f plus g, you expand it as its power series, you will get the sum of the power series. Okay, and this would be valid for the same values of x. Okay, now, we haven't proved that. What would it mean to prove this? It's not the most obvious question in the world, is it?
Could you use Taylor's formula and take derivatives of this proposed solution, or derivatives of the sum, and show that it is this based on Taylor's formula, something like that?
Okay, so I think that would work. I think there's I think there's an easier way. Okay. What are we trying to claim here? We're trying to claim that this equality is true, right? On the left-hand side, we have some well-defined thing. It's the function f plus the function g. We know what that is. We were given f and g. On the right-hand side, we have some series. So this is a statement about the sum of this series on the right is equal to the sum of these functions on the left. Okay? Now to prove anything, anytime we say the sum of this series is, what that really means is that the limit of the partial sums converges to what we're claiming the series is equal to. Oh, sorry, Benjamin, I just saw your chat. Yes, we are trying to get to the fact that there's linearity in adding power series. Okay, so what would we prove? Right, really what we want to prove is that we look at the left-hand side, we subtract off the power series, sorry, the partial sums of the right-hand side, take a limit as our partial sums go off forever, k goes to infinity, and we get 0. Okay, that's what it means for the sequence of partial sums to converge to the sum. Okay. Now, I'm not going to wrap this in a formal proof thing, but this is essentially a proof. On the left-hand side, we can regroup this. This would be f of x minus the sum up to k of the power series for f and then g of x minus the sum minus the power series for g, the partial sum of the power series for g. Okay, we can use a triangle inequality. This is less than or equal to the two limits added together. Okay, I'm trying to rush through this. My point with this is just kind of to show you what this argument looks like. Okay. And I claim we're done. Why are we done?
Because we have, we sort of suppose that these are true in the beginning by saying that there's a power series.
Right. We said that this power series of the ANs converges to F, and the power series of the BNs converges to G. So both of these limits are 0. Okay. Now there's one thing that we need to make clearer than we have, because we kind of ignored it. What is x here in our proof? What do we want x to be?
Well, it's within the radius of convergence, right?
Yeah, so what we want to say up here is we want to fix an x at the beginning. Okay, so for a particular x in this radius of convergence, we have, okay, and then here's the series we claim is equal to the sum. Here's the sum of the functions. We showed the limit is 0 for that value of x. Okay? And therefore, we're done. Okay? For any x in that open interval, indeed, the sum of the power series converges to the sum of the functions. Okay, we good? Any questions on that?
Why are we doing the absolute value here? It seems like it's kind of unnecessary.
So, like this absolute value?
Yeah. I guess so we get equality to 0.
So that absolute value is the distance in R. That's the distance on the real line.
Okay,
we're trying to prove that this sequence, the sequence of partial sums, converges to this value, which is the sum of the functions. Okay, so you're proving a sequence goes to a limit. You want to prove the distances go to 0, but we're on the real line, so our distance is absolute value of 1 minus the other.
okay.
Does that make sense?
Yeah. I'm just, yeah, okay, yeah, I got it.
Good.
Okay.
Okay, so if we got two functions that both have power series, we can add them. Good. We could also multiply by a scalar. So the set of functions that have a power series, say at the origin, is a vector space over the real numbers. Okay? If you take an abstract algebra, you might want something a little bit more. You might want a ring. Or even if you haven't taken abstract algebra, you know about the operations we can do with numbers. You might want to multiply two power series. So that's the big theorem today. Can we multiply power series? Okay. So what I'm going to do is we're actually going to state this as a theorem. I'll be a little bit careful here. We got two functions. Okay. We're going to be interested in the open interval from minus r to r, so we need to assume that they're both defined there. Let's say they're both analytic at the origin. And let's give them power series expansions. Okay. So far I've just been a little bit more formal about the same setup that we had last time. Now what about the product? This is the conclusion of the theorem. Then their product, which would be a function fg. Now, we know the functions f and g are both defined from the open interval into the reals. So we have no problem defining their product also as a function from that open interval into the reals. The product is a well-defined function. There's no problem there. Okay? Let me maybe write in red what we're actually claiming. It's also analytic at the origin. And we're claiming a certain formula for it. I will write it in the least motivated way possible first. Okay. Where does that formula come from?
Well, we can just pair up the coefficients in both power series.
Mm-hmm. So if we just expand out the power series and multiply them like they're polynomials, that's what we'll get. Okay, we multiply them like they're polynomials, and then we collect the terms according to their powers of x. We're going to see more. We're going to see that in just a second. Just for the interest of time, let me start the proof, and then we'll get to that. We'll see why the formula makes sense in about 3 lines. Okay. Now, we're going to need partial sums of f, partial sums of g, and partial sums of this product series. Okay, so we're going to define f sub k. We haven't used this yet. We've usually been doing s as our partial sums, but since we're going to have 3 different partial sums here, we need to associate with which function they are. Okay, so f sub k will be the sum up to the kth term of f. So it would be the sum of an x to the n up to the kth term. We'll do the same for g. Okay. For the product, I'll call it h. Okay. Now for f and g, we really had all the powers up to and including x to the k. So what we want here for the h sub k, I want this to be, I'll write it in words first, all powers up to x to the k of what we get when we multiply those 2 power series. Okay. Now, like we said just a couple minutes ago, we're going to pretend the power series are just long polynomials and multiply them out. So right here, we've got an a0 plus an a1x plus an a2x squared, etc. Right here, we've got a b0 plus a b1 plus a b1x, sorry, plus a b2x squared, and so on. Okay, so first let me do it without a summation sign. Let me get the lights first. Okay, so we're going to do this without a summation sign first. Constant term is only a0, b0. It's the only way you're going to get a constant term in that product. Then we'll have linear terms, a0, b1, or a1, b0. Then we'll have quadratic terms, a0, b2, or a1, b1, or a2, b0. Okay? And we keep going up until we stop at some coefficient of x to the k. Good so far? Okay. Let us group, no, we're not even grouping anything. We have the same order on terms now, but we're going to write it with summation signs. So this would be the sum where the power is n and we go up to k. And now you can see kind of what's going on. The subscripts of the a's and the b's have to add up to n. And it's any possible way to get two numbers that add up to n. So we might as well call m the subscript of a, and then b would be n minus m. And that would be the coefficient of x to the n. Okay, now, it's very similar, the two things I just highlighted in green, except the one in the proof is a partial sum and the one in the theorem statement goes on forever. Okay, but that's where the one in the theorem statement is coming from. It really is just if you expand these out and you just multiply. Okay. And you might think, why is there even anything to prove here? I mean, we know that the series for F converges, the series for G converges. Why do we even have to show this? Isn't it obvious? And the problem is that these are infinite series, and there's no guarantee that we can shuffle things around and add them this way or that way and have it all work out. Okay. With me so far? Now, we're going to do a little bit of unmotivated algebraic manipulation. Kind of the only, I can justify it once we get to the end of it, and you can kind of see why we did it. It will probably never quite make sense, why you would think to do it, except you might just play around with different things. Okay. The first thing we're going to do is rewrite this in a completely different way. Instead of breaking both F and G down into their individual terms, we're going to break G down to its individual terms, but we'll let F be represented by its partial sums. Okay, so what I mean by that, if you're looking for, again, remember, this expression is only powers up to x to the k. So if you're going to have powers up to x to the k, you could allow the partial sum f naught of x the partial sum f naught of x is all the powers up to x to the 0 of x. It's just a naught. That one will show up. I see. So the way I really want to say this is we are going to group by the coefficient of the power series for G. Okay, so let me actually write it that way instead. In here, we are going to have, we'll do it this way, how about? In this sum, and you probably shouldn't think about the summation version I've just written, you should go back up to here. Here we go. Yes, this is the way to explain it, I believe. You're going to see a bunch of terms with a B naught. What are those terms?
each term would just be the highest order A available for that degree, right? A1 be 0 for the linear term, and then A squared be 0 for the x squared term.
Exactly. So here's a B naught. It comes with an A naught. Here's a B naught. It comes with an A1x. Here's a B naught. It comes with an A2x squared. Okay, keep going. You're going to come up to, in here, there's going to be a B naught. It's going to come with an AK, x to the k. Okay. So really what you're getting is you're getting a B naught with its power of x times all the powers of the a's up to the kth with their powers of x. Okay. Now you go on, what are you going to get with the B1? You are going to get an A naught. You're going to get an A1x, etc., 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 except you're going to stop this time at an AK minus 1 x to the k minus 1, because you're not allowed to go over the kth power. So you will get the k minus first partial sum of f. Okay. And you're going to do this up until you get to bk x to the k, when you will get the 0th partial sum of f. Okay, so we just regrouped the terms. When you have an infinite series, you're not, we haven't gone into this too much in this course, but you might remember back in Calc 2, when you have an infinite series, you're not allowed to go rearranging the terms like this. But we don't have to worry about that. We have a finite series. Okay? There are only finitely many terms in this thing we're rearranging. So we're allowed to rearrange finitely many sums however we like. Okay, any questions so far? Okay, good. Now let's write this in summation form. Okay. Except I want to do it kind of the opposite of how we just wrote it. I want it to be fj of x. And we see we are going to start at an f naught and go up to an fk. Okay. So we're going to go up to an fk. And our b things are going to start at a bk, x to the k, and go down to a b naught, x to the naught, x to the 0. Okay, that's just algebra. Questions? Okay, all we've done is algebra with finite sums so far. Okay, what do we want to prove? Well, we probably should have maybe said that earlier. Let's fix an x in our open interval. What do we really want to prove? We want to prove that the limit, as k goes to infinity, of this thing, this h sub k, this is the kth partial sum of our product series in the theorem, minus the actual value of the product of the functions. We want that limit to be 0. Okay? That would mean that for any x in this open interval, this series that we claimed was actually the product is indeed the product, and we'd be good. Okay? Okay. Oops, not the tool I wanted. There we go. So in this limit we want to evaluate, we've got a product. Sorry, we've got an HK, and we have this expression for HK, which is the one we're going to use. Good. We want to fit, somehow we want to relate this to F and G. We've got all this convergence going on, but we just kind of have to take it apart in a particular way. So I'm going to do kind of a weird thing. What we're going to do is we're going to relate HK to F times GK first. So I want to look at what is f of x, gk of x. That's the value of the function f at the point x times the partial sum of the series for g. Well, we'll just move the value of the function f into that sum, and we'll see that this is literally f of x times bn x to the n. Okay. Now, if you want, you can expand that out. What do you get? You see that you've got an f of x b naught, f of x b1x, all the way up to f of x bk x to the k. Okay. Now, in our expression above, we've got bk's and xk's, except they're going backwards. Right? In this sum, we are counting down from bk x to the k down to b naught x naught. So what we actually want to do here is reindex this series backwards. Okay? That is pretty easy. We make a new variable, we call it j, we make it, I'll do this in green so it's clear this is kind of a parenthetical. We make it actually n minus k, and in that case our old summation value n would be j minus k, and we would end up summing from j equals 0 to k of f of x times b k minus j x to the k minus j. Okay, and you can check, if you expand it out, you'll get the same thing. I'm not lying that we haven't changed anything. Here we have yet another finite sum. It's got an f in it, but remember f, we're thinking, f is just a function, so f of x is just a number. Don't think about f as being equal to its power series unless we want to do the expansion of it. So here's what we're going to look at. We want to eventually look at hk minus f times g. But as a step along that journey, we're going to look at hk minus f of x gk of x. Now you see, we've just got two series in the same summation variables. We can just combine them, okay? They both got the same coefficients of b's, the same powers of x's. Now one of them has an fj and the other has an f. That's the only difference. So I'm going to subtract one from the other. I'm going to end up with a sum from j equals 0 to k of fj minus f of x times b sub k minus j times x to the k minus j. Okay. So far I'm just doing algebra with finite sums. Please interrupt if you have any questions.
So the strategy we're doing here, I sense a strong triangle inequality coming. We're showing that these are close and then the other two are close as well.
Yeah, yep. There's going to be a lot of triangle inequality. Although first we have to get to what we're actually interested in.
Okay.
So what are we actually interested in? Not this one, we want hk minus fg. Well, let's express that in terms of the one we've just expanded. Okay. hk minus fg would be hk minus fgk and now to get from there to what we care about, we want to add an fgk and subtract an fg. So really that would be adding, they both have f's in them. We would be adding an f times, we want to add back in the gk and subtract off the g. Okay, are we doing good? Well, if you're happy with the sum we got above, and by the sum above I mean this guy, then yes, we're doing good. We've expressed the thing we care about. This is the thing we want to make small, go to 0, actually. We've expressed this in terms of the sum above, plus f of x, which, remember, for our purposes, f of x is just some number. Okay, f is a function, x is just some number in its domain, f of x is just some number, times some gk minus g. Now, gk converges to g, that's what it means for g to be analytic. So that thing's going to get small. Okay. So this thing on the far right is definitely okay. Okay, because we have pointwise convergence of the gk to the g. and fk is just some number. So we can make that as small as we like, right? So I hope you'll grant me that there is some capital K such that for little k, at least capital K, we have that thing on the far right is just small. Okay, I realize we haven't defined an epsilon. We need to define an epsilon. I'm going to just go right up here. And add in. I will highlight it in green. I'm going to let epsilon be arbitrary. We want to make our thing less than epsilon. Okay. And again, we got this because that thing's going, the gk minus g is going to 0. Because g is analytic here. So it's equal to its power series. Okay. Now, it remains just to bound our sum. Not that sum, our sum. So now we want to show this sum let's also make that less than epsilon over 2. Okay? If we can do that, we're done. Because epsilon was arbitrary, and that will mean that we've shown that our series converges to the product as claimed. Okay. Let's just think about expanding this series out. This sum is f0 minus f. I'm going to drop the of x, but I hope, that's still there. Times bk x to the k plus f1 minus f bk minus 1 x to the k minus 1 up to f k minus f times a b naught x naught. Why is that going to be small? In fact, not only do we want it kind of small, we want it to go to 0 as k goes to infinity. Why is that going to go to 0 as k goes to infinity?
I actually don't see why it would. So I'm looking at this first term, and the f's are still going to be, it's still going to be f of 0 minus f of x, so that's going to be constant. But this bk, I don't see why it can't just explode and grow it to as big as I want it to be to make the sum not small.
Mm-hmm. Well, what do we know? We know the sum
Ah.
converges.
Okay,
So,
so we can't get the b's as big as we want. Okay,
the light. 1 second. Okay, so we know the series for g of x converges, so the individual terms have to go to 0. So for k large enough, those are going to be small, right?
right, and then the other ones are just a number that's not gonna change based on k.
Well, here's the problem. What are we going to do about this guy? B naught is just a number. So how is this term small?
The fk,
Yeah.
the fkf, that'll get small.
Yeah, so this is neat. Here we've got a sum. It's a long sum. In the first portion, I shouldn't say half, but it's, sort of half. In the first portion of this sum, the terms are getting small because the b's times the x's are small. In the second portion of this sum, the terms are small because these differences in the f's are small. Okay, so what we're actually going to have to do is somewhere in here, we're going to have to make a division. We're going to say over here, these are small because the partial sums of the f's converge to f, and these are small because, and I shouldn't use k here because k is in our, let me use different variable. There's a j. How about I? It's small because fi is converging to f, and these are small because bi x to the I is converging to 0. Okay, so these guys are small because of those things, and on the right they're small because of those things. Okay. Now, I realize we're out of time. So I can't show you the actual inequalities that we'll want to insist on to get our bounds. They'll be in the lecture notes, but I hope this gives you some idea of how this proof goes. Right? We break it into 3 pieces. Remember, there was the piece before that we already bounded. Break it into 3 pieces, we bound all 3. That's why I said this is a really real analysis-y proof. Just breaking things into pieces, making all the pieces small. Okay? And what do we get as our reward? We get the fact, where's our theorem go? We get the fact that we can multiply power series, and the product is exactly what we think it should be. Okay? Like I said, if you've taken complex analysis, this is completely trivial once you build up the power series machinery in complex analysis. And the point in complex analysis is that the singularities of the product are just the singularities of f or g. There can't be any new singularities pop up. Okay, but that proof doesn't work in our context because we're on the real line. And so, unlike complex analysis where you can say, okay, my radius of convergence actually has a reason, and that reason is a singularity in the complex plane. Here on the real line, we can't talk about that. So we have to talk about actual convergence of series, and so this is the proof in this context. Okay, well, I hope you have a great weekend. Like I said, once the lecture notes are posted, which will probably be kind of late-ish today, You'll get to see those actual estimates at the end, and, but that's it. And I will see you all on Monday. Bye-bye.